Hello, math nerds. It's the crazy math nerd here, Kitty Morgan. Wow, we've been looking lots of graphs and talking about limits, and now it's time to take an algebraic approach to limits. Um, I will tell you though, the more you know about graphs, the easier the idea of what we're fixing to do is. And we've already talked about some places where limits are just nice and easy. And then we've talked about places where limits are not nice and easy. And if we can recognize that those things will happen in certain functions, it's really going to help our analysis. So here we go. So let's look at example 1a. It says the limit as x approaches -2 of this function. Now, it's going to be very helpful if I know what this function is. Well, this function, I don't know what my pen's doing, y'all. It's crazy. This function right here is simply a parabola. Okay, what do you know about a parabola? A parabola is nice and smooth. It's a polynomial. There are no breaks or anything. So just like in the last video when we were talking about the basic functions, if you couldn't quite see on the graph what it was, you could just plug in the x and get the y. And why could you do that? Because this is a nice, smooth, continuous function at all places. So if that's true, just plug in -2. So here I go. -2 squared minus 4 times -2 plus 1. -2 squared is 4. Minus is plus 8. Plus 1 is lucky 13. Yay! So the value of the parabola at -2 is 13, and the limit is also going to be 13 because that is the y value that the function will approach as it goes to -2 from both sides because it's a nice, smooth, continuous graph. Okay? How about the next one? Well, oh no. You know, when we have rational functions, we just have to be on the lookout for bad people, right? If that's ever 0, if that x minus 1, that denominator is ever 0, we are in trouble. So, and we know that because anytime the denominator is 0, we're in trouble. So, let me think. What could I put in for x to make that 0? That'd be 1. Are you going to 1? No. See, you're going to -1. So, I have to be cautious and I have to analyze it, but once I figure out it's not the bad place, just plug it in. So, here I go. So, 2 times -1 minus 6, it's like a tilde, over -1 minus 1 is -8 over -2. I think. I hope so. And that is 4. So the y value of this rational function at -1 is 4. And because it's not a place where there's a vertical asymptote or anything else, it's just a nice smooth place. There is a vertical asymptote at 1. But that's not what we're asking the limit of, so we're good. That value's 4 and the limit's 4. Cool. Are you telling me that calculus is all about just plugging in some numbers and getting a y value? Sometimes it is. All right. So let's plug in pi. Oh my goodness, I've got to know the unit circle. So 2 cosine of pi minus pi over pi plus 2. Now, why am I not worried? Is pi going to make this denominator 0? No, so I'm not even worried. I'm not worried. I ain't scared. All right, so cosine of pi is -1 minus pi over pi plus 2, which is -2. Let me go over here. Which is -2 minus pi over pi plus 2. And y'all, I think that that's going to be nicer because if you take a negative out of the whole thing, don't those cancel? Boom, boom. And you get -1. So the limit is -1. So most of the time, I'll say most of the time, if you are taking the limit as you go to a number, you're just going to evaluate the function at that number. And if you get an answer, you're probably pretty good. Okay? I know that seems so simple, doesn't it? So I plugged in -2, got 13, plugged in -1, got 4, substituted pi in for x, got -1. Normally, there are a few exceptions, we'll talk about those later, but that's like crazy stuff. So normally, if you're going to a number and you have if your limit is approaching a number like -2, -1, or pi, then you just plug it in and see what you get. If you get a number, most of the time, 99% of the time, that's the answer. So I'm going to go with that, and I'm going to do example 2a, and here I go. I'm going to plug in 2, so I get 2 squared minus 2 times 2 minus 8 over negative, oh, that's a -2, isn't it? Oh, lordy. I missed that little negative part. Sorry about that. Over -2 plus 2. And I'm just going, ooh, I'm going to get an answer, and I'm going to be done. And I get 4 plus 4 minus 8 over 0, which is really 0 over 0. All right. When you get this, that means that there is a hole in the graph. A hole in the graph. There's a hole in the graph. Hole in the graph. I don't know if you remember that from pre-cal, but when you get 0 over 0, that means there's a hole in the graph. But we know from all the graphing stuff we did, if you have a hole, you still have a limit because it's where that's the y value of the hole. So what we're going to do is we're going to find out where the hole is. And the way you do that is you factor. Now, y'all, if you have x plus 2 in the bottom, I should have been scared right there because if you put -2 in, you get 0, right? So that's a little, whoo, be careful. And if you get 0 over 0, that means you have to have a common factor if it's polynomials. If it's other things, and you've got to do a lot more algebra. But if it's just polynomials like, a parabola and then a line on the bottom, then one of the factors will be the factor on the bottom. That's how you get 0 over 0. So now I've just got to figure out what this factor is. Well, the only number that you multiply times 2 to get 8 is 4, right? And to get a -8 and a -2, that has to be -4. So if you're not a great factorer, there's a hint to one of your factors, and it makes it easy to find the other factor. Crazy, right? Once you cancel it, now you're going to evaluate this new piece at -2. And so that's going to equal -2 minus 4, which is -6. So what does that mean? That means there, and I'm going to write way over here because I want to, there's a hole at -2, -6 in the graph. There's a hole. That's what that means. And if there is a hole, then if you come in from the left and from the right, you get the same y value, which is -6. So if you have a hole in a graph, you will have a limit because both sides are approaching it, even though they can't actually get there. So -6 is both the limit and the y value of the hole when you do this. Isn't that crazy? I know, right? And one more example, and I'm going to erase this now so I'll have some room. Erase this at least. Is I'm just going to plug it in just like normal because that's normally my approach. And plug in is not mathematically correct. I'm going to substitute in the value in for x. So when I do that, I get 0 minus 0 over 0 plus 0, which is 0 over 0. But that is not a value. That's called an indeterminate form. So for simple polynomials like this, the best way to find the limit is to factor, cancel, plug back in. Oh, that sounds like a cheer, doesn't it? So I'm going to factor out a 5x on the top, and that gives me x squared minus 1 over x times x plus 1. And this x squared minus 1 should probably give you some kind of craziness going on here. And so, first of all, the x's cancel. Oh, they do cancel, so we're good. Heck fire. Let's go. So plug 0 in and you get 5 times negative 1 over 1, which is negative 5. And that's your limit. There you go. Love it. Now, there is a vertical asymptote at negative 1. I know that because that's what would make the denominator 0. But I'm not asked about that, so I don't care. So just a FYI, don't get upset about things you're not asked about. Okay, well, that was fun. All right, now, there's one more situation. So either you evaluate the function at a number and get a number. So you evaluate the function at a number and get a number, or you evaluate the function at a number and get 0 over 0, factor, cancel, plug back in. Okay? Or here's the other situation. So I'm very leery of example 3a because I see this guy on the bottom in the denominator, and I go, if I plug that 2 in, it's going to be 0. I mean, that should make you just, alarm bells should be going on. So I'm going to plug it in just like I normally do, and evaluate it, and I'm going to get 4 plus 5 over 0. So in this case, I actually get a number over 0. And if you get a number over 0, that's not a whole, that's a vertical asymptote situation. So if you have a vertical asymptote, you're either going to have both sides running up, both sides running down, or both sides of the graph running in opposite directions. We've seen all of that in the graphical stuff we've talked about. So how do you figure it out? Well, let's do a little analysis here. All right, here's 2. If I put a value really close to 2, but to the left end, like let's just say I put it in there, that would be positive, but that would be negative. So that means that the graph on the left is going down forever at 2. If I put something to the right of 2, but really, 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 really close, that would be positive on the top. I don't know what it is. It doesn't matter. It's positive and negative. And this would be positive as well. So on this side of 2, it's going up. And I don't know what it's kind of doing everywhere else. And I don't care because I really want to know what's going on at 2. So if one side is going down and the other side is going up, I know there's a vertical asymptote, but if they're going in opposite directions, we say the limit does not exist, right? Because they're not going in the same direction. We know, number one, there's not a limit. Because if you have a vertical asymptote, a graph has to run up and down that vertical asymptote. That's why we have vertical asymptotes. So your job is to figure out, do they go in the same direction or opposite directions? Right? So again, look at 3b. I'm a little worried about 3b because I know 0 makes that 0 into that x would make that 0 in the bottom. So if you plug 0 in, you get 4 over 0. This means you have a vertical asymptote. But we know something about this graph. We know what 1 over x squared looks like, and if you multiply it by 4, all that does is make it like just pull away from the axis. It makes kind of pull away. Oh, I'm sorry. Hello, let's draw the right graph. Come on, crazy woman. Like that. That's 1 over x squared, but it just pulls it away. Like it pulls it away, the 4 does that. So if you're going to 0, coming in from the left, you're going up forever. Coming in from the right, you're going up forever. So there is no y value that it approaches. There is no limit, but both sides are going in the same direction. So we say that that limit is positive infinity because both sides, well, let's do this right, because the limit does not exist. And if the limit does not exist, that means there's not one y value that the graph is approaching as it goes to 0, does not exist. I'm trying to talk and write at the same time, not working right now. And then 2, the graph is going in the same direction, is going up forever. Graph is going up forever on both sides. That's what that means. Okay, so we have done all of the kind of simpler cases of what happens if you are finding the limit as x approaches a number algebraically. So plug it in. If you get a number, that's probably it. If you get 0 over 0, let's go back down here. You've got a whole, if you get a number over 0, that means you have a vertical asymptote and you have to figure out, are both sides doing the same thing? That gives you an infinity answer, or are they doing opposite things, which means you have a does not exist answer. All right, thanks so much. Hope this helped. Have a great day. Bye-bye.